then we take a look at question 2. Question 2, for the first step, right? For the first step is what? For the first step, this step, we need to go to check. Step 1. Step 1 is what? It's sin addition. To get what? Cis product. Because it's addition, it will it will convert alkyne to alkene. To cis alkene. Okay, to cis. And then the structure should be like this. Not much change because, yeah, this is the same. Oh, no, let me see. There's double bond. Oh, it does not matter. It does not matter here. Anyway, here it does not matter because what? There are two hydrogen. For this carbon, there are two identical hydrogen. So there's no cis or trans, right? Remember, there's no cis or trans. But we know it's a cis product. But here it does not matter because you have the same. You have two identical groups attached to a same carbon. So there's no cis or trans. Okay, there's no cis or trans. And then the second step is what? The second step, step 2. Start from here, and we what is a hydroboration and then oxidation. Is anti-mark. Is anti-mark. So it's anti-mark. Anti-mark. Then the hydrogen will sit here. The hydrogen will go here, right? It's anti-mark. Anti-mark. Then the hydrogen will go to the carbon with the least hydrogen. Hydrogen here, OH group will come here. So the answer should be E. Okay, so I will skip question 3 because you can find the answer from the slide. Okay, you can find the answer. First, question 3, I will just say first, question 3, first, addition. Step 1. Step 1 is addition. And then step 2 and 3, what? Will convert to alkene, to alkyne. To a compound with carbon-carbon triple bond. So the answer is B. I think there's no E. I don't remember exactly. Could be no E anyway. Here we discuss question 4. Question 4. Question 4. Trans, right? Reaction. Question 4. Question 4, right? Is trans to hexene. trans 2-hexane. And then a solution of bromine in carbon tetrachloride. Is addition reaction, right? Is addition reaction. Is cis-O trans. Is trans addition. Why is trans addition? Because bromine is big. Bromine is big. So these two bromine need to stay away from each other. So it's an anti-addition. And then anti-addition will lead to what? Trans product. So these two bromine will be opposite. So if we use, you see, these two groups will stay as trans. Because we start with trans, they will stay as trans. And then these two bromine should be trans too. Then one bromine is here, then the other bromine should be like that. Or the other way, so or bromine is here, and this bromine is here. These two groups stay as trans, okay? And these two added bromine should be trans too. Why? Because they're too big. And because of the reaction mechanism, they need to stay away from each other. And then you can see the answer should be compound 3 and compound 4. So this is compound 4. Okay, this is compound 4. And this is compound 3. So the answer should be C. And I purposely put the question 4 and 5 together, right? Because here the reaction is in what? Is in this. And then, if you see that here the solvent is this, bromine in carbon tetrachloride. And here the solvent is in water. And then we will form this, where the bromine is partially positive and this is negative. Why is that? Because if you check the electronegativity table, the electronegativity number for oxygen is larger than bromine. Therefore, oxygen will take electron, will share more electron from bromine. Therefore, bromine is positive. It's positive. Oh, well, that's okay. Yeah, we are all both focused. That's okay. So you see, this is positive, this is negative. That's one thing. While at the same time, there's another one. It's anti-addition. That means these two groups need to be what? To be trans. Need to be trans. You see, either bromine is, when bromine is above the plane, OH is behind the plane. Or, oh, sorry, I drew one more carbon. see, they are obviously they are enantiomers. Obviously, they are enantiomers. So here, I mean, only A is only A, but there should be another one. So yeah, we need to pay attention to this. And then here is, I mean, here it should be also what? Marker addition, right? These two are two different things. This is what? This is radial selectivity. This is stereo selectivity. They're different. This tells the positive charge, the positive group should go where? And then this anti-addition tells how these two groups are related to each other in terms of space. They're different. They're different. So, question 6. Question 6. Well, maybe I just put here. Okay. Question 6, right? The first step. Step 1. Step 1, we check is anti-addition. Okay. Anti-addition. And then we start with alkyne. The product will be alkene because it's anti-addition. Then the two group should be in trans. Then we get okay. You see, trans. They should be trans. This is step 1. And then step 2, you see that the second step what? Use what? Use carbene, right? Use carbene. Carbene. It will form a 3-member ring. This group will be added to this double bond. And these two trans will stay as trans. Okay, will stay as trans. And then here, they need to be stay as trans. So then this will become 6. Or the other way. Or this is, sorry. This is above the plane, this is behind the plane. They need to be trans because they start with trans, then they end with trans. So for question 6, is very obvious, right? You see, we pay attention to this. It's cold condition, potassium permanganate, cold condition, and dilute, cold and dilute. Then we'll get what? We'll get syn addition. We'll get a syn addition of 2 hydroxy groups. Syn addition of 2 hydroxy groups. OH group to the double bond, to 2 carbon in a double bond. Syn addition. So the answer should be C. Okay, should be C. Surely it can also have, a what? A enantiomer. Okay, here just give one. So, any question? And then question 8. Question 8. We start with 2-butyne. Like that. And then step one. Step 1 is what? Is syn addition. Okay, step 1. Syn addition. Then to get what? To convert a triple bond to a double bond. And then the step 2 is also syn addition, right? So syn addition. So these two will stay. These two will stay cis. And then these two hydroxyl group and you can easily see there's a mirror plane, right? There's a mirror plane. There's a mirror plane. There's a mirror plane. Then this one should be a chiral, not chiral, even though it has 2 chiral center. You can easily see. They should have opposite chirality. Or if you want to check, that's okay. No, okay, here we'll check. Okay, we'll check the chirality. Then there's a hydrogen behind it, right? There's a hydrogen behind it. You see, these 2 bonds are like that. Then these 2 bonds are like that. Then, because we always remember, here, tetrahedral shape. Okay. Yeah, we can do that. You see, if you put these 2 bonds, these 2, this 1 bond, another bond, these 2 bonds, you put 2 bonds in this plane, then there's one should be like that, right? The OH group should be here. The OH group should be here. And then the hydrogen should be here, like that. Because it's tetrahedral shape. And then when we want to determine the chirality, we always want to what? We always want to look so that our ions and the chiral carbon and the hydrogen are in the same line, while the hydrogen is away from us. Ions, chiral carbon, hydrogen. Okay, then we can draw. Surely this priority number is 1, right? It has highest priority. Okay. What about these 2? This should have the second highest, right? This group. And this should be the 3. So if you look at this way, the OH group top, 2, 3. So this is clockwise. then it's R. So this one should be R. And this one, because there's a mirror plane, this must be S. And we can check, this must be S, because there's a mirror plane. And these two parts are mirror images of each other. Then their chirality will cancel each other. Then this is a chiral, this is a chiral compound. Not chiral, okay, we put symbol. Sometimes we put a chiral. This is not chiral, okay, it's not chiral. Why? Because it's a methyl compound. It's a methyl compound. Okay. According to the symmetry, this must be S. Let's check. Okay, let's check. Let's check. So here again, we always need to have this in our mind. Okay, you see that this hydrogen should be behind the plane, right? And these two bonds are in the same plane, And OH group is like that. OH group. This is hydrogen behind the plane. Okay. Then we view this way. Then again, OH group on top. And then this group on the right. But this is what? 3, right? This is 2. You see, this is 3. So 3 here and 2 here. You can see this is anti-clockwise. It's S. It's S. So these two have opposite chirality. Then, you see, from the symmetry, we can see. There's a mirror plane here. I mean, this is wrong, because these two hydroxyl OH groups should be attached to different carbon. So this must be wrong. And you take a look at this one. There's a mirror plane here, right? So this should be the correct answer. Should be correct. And then we can double check. We can double check whether they have the different, whether these two carbon have different chirality. So we'll so these are hydrogen. So there are different ways of figuring out this chirality. You can, either this is out of plane, but you can imagine you are on the other side. Then this hydrogen is behind the plane, right? You can do that, but you may find anyway that you feel more confident. To myself, you see, I prefer to change because this hydrogen is not behind the plane. Then I make it behind the plane. Okay, I make it behind the plane, and then I do switch. But we need to keep in mind, once you switch, the chirality. Once you switch any two groups, the chirality switches also. Then we do first switch. Okay, we do first switch. So we do first switch. We do. Okay, do first switch. I put the hydrogen behind. And then we can see. Okay, these two are in the plane. And we can name the priority number. Okay, surely these have highest priority, right? Because these are attached to oxygen, and oxygen has a higher atomic number than carbon here. And then you see this carbon is attached to OH group. So this carbon should have priority number 2, and this 3, right? 3. And then we can see, okay, this is behind the plane. And then we can just imagine, you see, in tetrahedral shape. We only need to keep this tetrahedral shape in your mind. Okay, tetrahedral shape, tetrahedral shape. Right, this is hydrogen. You see, now we have these two in plane, in the same plane. And then the hydrogen is behind the plane. And this metal group is above the plane. Then we view so that the hydrogen is away from us. Once we view this way, so we have this, which one? We view this way, right? And then this 3 should be on top. And then 1 here, 2 here. So this is S. Then this is S, but then we need to switch back because we did a switch here. This is S, then this must be R. And according to the symmetry, this must be S. This must be S. But we can also double check. Again, I will do the change. I will do the switch. Because this hydrogen is out of plane, then I will exchange it. Then we get this OH group here, and methyl group here, and the hydrogen here. And so these are so this is priority 1, right? These are attached to OH, so this carbon is priority 2, and this priority 3. Again, we put these two bonds in the same lane, and then we view so that our I's and the chiral carbon and hydrogen in the same line, and the hydrogen is away from us. Then we draw. Okay, if you view this way, right, it's like that. So the hydrogen is like that. So these are 2 bonds in the plane. This hydrogen is away from us. It's away from us. It's kind of confusing because you see, oh, the hydrogen is here. The hydrogen is not here actually. The hydrogen should be behind the plane, but we have the hydrogen is somewhere here, but we cannot draw that way. But we need to keep. We have this tetrahedral shape in our mind. That's a tetrahedral shape. So the hydrogen, you see that? The hydrogen is more like here. The hydrogen is like here. To be more precise. Yeah, it's like that. Instead of here. But when we draw, we don't, I mean, it's correct if we draw here. As long as we put this label to indicate hydrogen is behind the plane, we are good. But we need to know the hydrogen is not here. The hydrogen is not here. And then you view from this direction. Okay, you view from this direction. So the hydrogen is away from us. Our eyes, carbon and hydrogen on the same plane. Then we view. Okay, we view this way. We view this way. If we view this way, this group is like that. And then 2 is here. And 1 is here. So this is R. But with this switch, then we switch back. This is S. Yeah, we already have this. The hydrogen is here. But very often, we draw here because it has more space. Even we draw here does not mean hydrogen is here. Hydrogen should be here. It should be this place, not this place. But people usually, find more spacious place to put. So we have to have this tetrahedral. You see these 4 bonds like that. We need to have this picture in our mind. And once you have this picture in mind, and then once we know this Then we know how to determine the chirality. Then we can find the correct answer. And sometimes we don't need to do this. Yeah, you see here. Here, when we draw, we see, oh, the structure is like this. There is a mirror plane, so it must be a methyl compound. There's a mirror. There's what we call symmetry plane. Same thing, symmetry plane. And then we can find, oh, there's a symmetry plane here. There's a symmetry plane here. So this is not a chiral compound. This is not a chiral compound. So what's the relationship between these two compounds? Just now we said this R, this S. That is what? It's a methyl compound, right? It's a methyl compound. Because there's a mirror plane. There's a mirror plane. So are these two mirror planes of each other according to this plane? Yes. Yes, okay, that's good. We'll take a look. So they look like mirror images of each other. Okay. So this is R, then what's this? This is X, right? And this is S, then this is what? R, right? They have the same connectivity, and they have the same chirality. So this is also methyl compound. Yes?
If they have the same connectivity and the same
Chirality?
does that mean that they're identical?
They are identical. Even though they look like they're mirror images of each other. But the thing is that this is not a chiral compound anymore. This is not a chiral compound. Remember in chapter 5 we discussed if there are n chiral center, so the maximum stereoisomers, maximum number of stereoisomers equals 2n maximum. But you see that but you can see here, right? You can see here. There are two chiral centers. There are two chiral centers, and these two looks like stereoisomers, but they're identical. They're the same compound. Why is that? Because they're not chiral. This is not a chiral. This is a methyl compound. It's achiral. This is also achiral. They are the same. They are the same. I know this could be a little bit confusing. You see, once we determine the chirality, we can never be wrong. So it's very, we have to know how to determine the chirality. You can see that they are mirror images of each other, right? These two are mirror images of each other. They have opposite chirality like this. They are mirror. Through the mirror, they overlap each other. That's the same. And then the chirality cancel each other. Then it's meso compound. Then these two are the same.